Hello. In this video we're going to talk a little bit about Lewis structures, what they are, and how to draw them. Okay, so let's say for example we have a nice simple structure like that of methane. I apologize for my crappy drawing here, but that's one of the things about using this hardware. It makes me draw like I'm drunk. Anyway, so this is methane. Central atom carbon with one bond to each of four hydrogens, and its molecular formula is CH4. So the idea is, given a formula, we want to be able to figure out the Lewis structure, which really shows how the electrons connect each atom together, what the Lewis structure for a given molecule is. Now you can see for CH4, there's really not many options you have. But when we get to something like, for example, something rather more complicated like sulfuric acid, we're going to need some rules to actually help us guide our structure drawing. And so that's what we're going to go through. So let's start off with a molecule such as, let's do ammonia, all right? Ammonia, NH3. Okay, so here are the rules. The first thing we need to know is how many electrons are we playing with here that we have to place on our structure. And when we talk about electrons, what we're talking about actually is valence electrons, the outermost electrons on each atom. So for example, for ammonia, all we do is find the valence electrons for each atom, and you know how to get that. I hope the valence electrons is just the number of electrons that corresponds to the group that that particular atom is in. So nitrogen is in group 5, hydrogen is in group 1, and there's 3 of them. So giving us a total of 5 plus 3, 8 electrons. So that means when we have a molecule of ammonia, we have to place 8 electrons either in bonds or lone pairs in order to give us our complete Lewis structure. And when we have a simple molecule like this that consists of 2 types of atoms, the first thing we want to ask ourselves is which is our central atom. And the central atom is pretty much always the one that can form the largest number of bonds. So when you look at, for example, nitrogen and hydrogen, and let's say you say, well, nitrogen has 5 valence electrons, so if I place those around my nitrogen here, there we are, I've placed 5 valence electrons, so that means my nitrogen has 1, 2, 3 places to bond, so it can form 3 bonds. Hydrogen, on the other hand, with 1 valence electron, can only form 1 bond, and that's, you'll always find hydrogen is always on the outside of a molecule because it can't be anywhere else. So in this case, it means nitrogen is our central atom. So there we go. I'm going to put my nitrogen here, and I'm going to put my 3 hydrogens around it. Now I don't really know, let's just assume that I don't really know how they're supposed to be arranged, but all I know is there's supposed to be 3 of them. The next thing you do is connect each of the 3 outermost atoms with the central one. And if you remember how many valence electrons are involved in 1 bond, of course it's 2, there's no prizes for guessing how many electrons we have used so far, and that's 6, which means there's 2 more to place. So we have to ask ourselves the question at this point. For each of our 2 atoms, have we satisfied its required number of bonds and its required number of outermost electrons? And this is where you want to remember something called the Octet Rule. Of course, octet meaning 8, meaning that every atom, essentially apart from hydrogen, helium, boron, and beryllium, wants to have 8 electrons around itself. So nitrogen fits that. Now, how many electrons right now does nitrogen have around it? Well, you'd say 2 here. If I just show the electrons in these bonds, there's 1, 2, 3, 4, 5, 6. Don't be concerned that nitrogen has 5 valence electrons. We aren't worried about that anymore. What we're worried about right now is, does nitrogen fit the octet rule? And the answer is no, it doesn't, because it only has 6 electrons. Now, can we place any more bonds around the nitrogens to fulfill those 8 electrons? Well, nitrogen wants to form 1, 2, 3 bonds, usually. And it's forming those 3. So we can't give it any more bonds. And if we can't give it any more bonds, we have to use lone pairs. Which means there's got to be a lone pair on the nitrogen here. So what that means is, around that nitrogen there are electrons going in 1, 2, 3, 4 different directions. Now, do you guys remember what the name of the geometry is, where there are electrons going in 4 different directions? That's tetrahedral. Okay, but if we're just drawing a simple Lewis structure, we can just show something like this, and that would be the Lewis structure for ammonia. Now, if we were to get specific about it and actually show the stereochemistry, then what we'd show would be something like this. We would show these 3 groups, or these 3 hydrogens, in kind of a pyramidal shape relative to each other, with the lone pair on top. Okay, let's look at another example. All right, let's move on to another slide. Let's say, for example, we were to do something like methanol, or perhaps what if we were to do, I'll just delete this. What if we were to do acetone? And that has a formula of C2H6O. Okay, well, let's have a look at methanol first. First thing we want to do is count up the number of valence electrons. Well, carbon's got 4, oxygen's got 6, and each of the hydrogens has 1, and there's 4 of them, which tells us there's a total of 14 valence electrons here to play with. If we were to do acetone here, let's see, we've got 2 times 4, which is 8, 6 times 1, which is 6, and then another 6 for the oxygen, which would be 20. All right. So you can see the number of electrons that you have to place actually varies per molecule. All right. So for methanol here, the structure is actually sort of given to us already. It says CH3, and whenever you see CH3, that always means, well, it always means what it says, a carbon with 3 hydrogens attached to it. Now, how many bonds does carbon always want to form? The answer is, of course, 4. So if 3 of the bonds to this carbon are to the hydrogens, we have potentially 2 other options about the other bond connected to the carbon. And that could be this hydrogen. And if that's the case, there must be an oxygen here. Now, what do you guys think about that? Does this structure here look okay? And I'm hoping you're shouting out, no, that's bollocks. Can you guys see why this is wrong, actually? What's the issue with this? And the issue is that hydrogen can't form 2 bonds. It can only form 1. Plus, how many bonds does oxygen want to form? Well, if you don't remember that, we can just do what we did for nitrogen. 6 valence electrons, so we just count around. And what we get to is 2 single electrons, therefore 2 bonds. Oxygen wants to make 2 bonds, and here it's only making 1. So that tells us that can't be right. And if that's not the right order, then this must be the right order. Okay? Now, 14 valence electrons we had to place. How many electrons have we placed so far? Well, we've placed 1, 2, 3, 4, 5 bonds, which means we've placed 10 electrons. So that means we have 4 more to place. Can everybody see that we have fulfilled the number of bonds for each of our atoms here? Hydrogen, oxygen, and carbon. So if we can't add any more electrons in bonds, where do we have to add them? We have to add them as lone pairs. So then we look at the requirements, the electron requirements for each atom. Hydrogen is happy with 2 electrons. That's all it can accommodate. So each hydrogen has 2 electrons around it. What about the carbon? Does that have 8 electrons around it? Well, it's got 1, 2, 3, 4 bonds, so 8 electrons. Yes, it does. How many electrons does the oxygen have around it? Well, that one only has 2. It only has 2 bonds around it, so therefore how many electrons is that? Well, that's 4. So how many more electrons do we have to place? Well, that's also 4. And we said before we have to place those in lone pairs. The electronic geometry of this would also be the same as for ammonia, because we have electrons going in 1, 2, 3, 4 different directions, which would be tetrahedral. But when we count up our electrons here, we've used 2, 4, 6, 8, 10, 12, 14. That is the Lewis structure for methanol. Now when we go over here, there is actually more than one possibility for a Lewis structure that we could do for this. So I said acetone before, but let's just see what we can do. 2 carbons, 1 oxygen. Now what we said before was, when you have one atom, or only 2 types of atoms, it's usually the one that forms the larger number of bonds that becomes the central atom. But because we have 2 carbons here, and both those carbons are the same, we can't really talk about a central atom. But we can get an idea that the hydrogens are more than likely going to be around the outside, and the carbons are going to be somewhere in the middle. And the oxygen's probably going to be somewhere in the middle too. So what if we were to say, why don't we give ourselves a couple of options here, okay? What if I was to do this, and I put my 2 carbons next to each other? Each of my carbons wants 4 bonds, sorry. And right now I have 1. So what could I put around this carbon? Well, I could put hydrogens around 1 carbon. So what if I was to do this? And I put 3 hydrogens around that carbon. Is this carbon now complete in terms of bonds and electrons? Well, the answer would be yes. And we've used 3 hydrogens, we have to use 3 more and an oxygen. So if I say 3 more hydrogens, is this how they would be placed? I'm hoping you'll say the answer is no, because then there's nowhere for the oxygen to go. So what about if I just place 2 of those there? And what could I put here? Well, we can do what we did over here and put an oxygen here and then a hydrogen there. Remember, the hydrogens are always on the outside. Now let's see, can we count up the number of valence electrons we've used? Well, it's 1, 2, 3, 4, 5, 6, 7, 8. We've used 8 bonds, which is 16 electrons, which means we have to place 4 more. The key here should be, well, over here I had an oxygen with 2 bonds but no lone pairs, so I need to add 2 lone pairs. And that is one valid Lewis structure for this formula. This is actually ethanol. But what if we weren't told anything about the structure? Is there another way to arrange these atoms and have the carbons sort of in the middle? Well, yes, there is. I could put this here, but do I have to have my carbons next to each other? Well, it actually turns out that no, I don't. How many bonds did we say oxygen can form? Well, before we said 2. So what about if we had something like this? Oxygen wants to form 2 bonds. Carbon wants to form 4. So I've got to put something else around here. Okay? And these, of course, would be the hydrogens. Okay? So here I am doing the 4 hydrogens here. Sorry, the 6 hydrogens. No prizes for guessing what I've got to put on my oxygen here. Because how many valence electrons have I used so far? Well, it's 2, 4, 6, 8, 10, 12, 14, 16. So I've got to use 4 more. So any time you see an oxygen that has 2 single bonds to it or 1 double bond, you've got to put a lone pair on there. Alright, let's look at one more. What if we had, for example, C3H6O? Okay, this looks kind of similar to C2H6O, but now there's something else going on. We have 3 carbons. So what could we do? There's actually a whole host of different possibilities here, but I'm just going to come up with one. I'm going to draw out my 3 carbons in a row. Now, if I were to say, if I draw on all the possibilities for where my hydrogens can go, can you guys count up how many hydrogens I could put here? Well, it could be 1, 2, 3, 4, 5, 6, 7, 8. I don't have 8 hydrogens, so something's going on here. So, how about I say, well, okay, I'm going to put 3 hydrogens here. Maybe if I put 2 hydrogens here, that will give me 5, so I've got 1 hydrogen left. And then what do I do? Well, I have 2 bonds I have to place. And how many bonds does oxygen like to form? Well, of course, that's 2. All right. So rather than having those 2 bonds going in 2 different directions, you can actually have those 2 bonds pointing in the same direction. And if we just step back a bit and just calculate our number of valence electrons again. 3 carbons, 4 electrons each, 6 hydrogens, 1 electron each, and oxygen, 6 electrons, so 12, 24. Remember what I said before about anytime you have an oxygen with 2 bonds to it, you got to put 2 lone pairs there? Well, let's just see if this actually adds up. Are each of the 3 carbons complete in terms of their bonds and their octet? Well, the answer is yes. Is the oxygen complete in terms of its bonds and its octet? The answer is yes. If all the hydrogens have a single bond, they're fine. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've done what we were supposed to do. Pat on the back. Good for us. So that's how to draw Lewis structures of neutral molecules. Now what about if some sneaky professor came along and said, well, that's fine. In fact, that's too simple. What are we going to do if I ask you to draw me the Lewis structure of this? It's got you stumped, hasn't it? Because what on earth do I do about these? Well, it turns out this is a hell of a lot easier than it looks, okay? Let's do one for a anion and one for a cation too. Okay. Now, the charges here, they only really come into play when we're counting up our valence electrons to begin with, okay? So carbon has 4 valence electrons. Each of our 3 oxygens has 6. So that's a total of 18. Okay. Now, -2 here means, what does that mean? Does that mean it's 2 electrons short or it's got 2 electrons extra? Well, 2 minus, because each electron has a negative charge, means there are 2 extra electrons there. So we're going to add 2 to that total charge. Well, that total number of electrons, sorry. So 4 plus 18 is 22, plus 2 is 24. Okay. And let's just go down here. Nitrogen is in group 5. There are 4 valence electrons, giving you a total of 9. Now, you've seen so far that in every case where we drew out a structure, we added our electrons in pairs, because each bond is a pair of electrons, each lone pair is a pair of electrons. So how is it possible that we can draw a Lewis structure for something that has an odd number of total electrons we have to place? Well, the fact is it's not possible. The plus charge here means one of my atoms has essentially 1 bond too many, and so it loses an electron because of that. And so I'm going to subtract 1 electron from my total. 8 electrons to place here. So just as the plus charge means one of my atoms has 1 bond too many, the negative charge means one of my atoms, or in this case possibly 2 of my atoms, have 1 bond too few. So let's do CO3 2- first. Out of carbon and oxygen, which do you think is more likely to be the central atom? Well, it's the one that forms the larger number of bonds, which is carbon. So here's our carbon, and I'm going to draw 3 oxygens around it. The rule said before, the first thing we do is draw a single bond between the outer and inner atoms like that. We've used 6 electrons so far. How many bonds does carbon want to form? Well, it wants to form 4. So what do I have to draw to one of these 3 oxygens in order to give my carbon its required number of bonds? Well, I have to draw a double bond there. Now oxygen wants 2 bonds. So can I do this and this? I'm hoping you'll say, no, that's silly. Now why would you say that's silly? Why is carbon with 6 bonds silly? Well, carbon only has the space around it to form 4, and only has 4 places in its valence shell where it can add 4 more electrons. Plus, it would violate the octet rule too. Now, we said before that the 2 minus here means there are more than likely 2 atoms which are not, which contain 1 bond less than they normally would. So let's see what we can do about filling in our electrons here. Because I'm hoping you guys can see there's not much more we can do about bonds at this point. The carbon's complete, this oxygen's complete, but we can't do anything with these 2 without compromising the carbon. It's okay usually to go 1 bond too few, but to carbon you can't go 1 bond too many. Let's try putting in some, well, let's see what else we have to do. We've used 4 bonds so far, so that's 8 electrons. That means we've got another 16 to place. That's a whole lot of electrons. Do we need to place any electrons around the carbon? Well, that would be a no. What about on this oxygen? Well, that would be 2 lone pairs there. Now this oxygen here, how many electrons does it want around it? Well, it wants 8. Now right now it only has 2. We can't form any new bonds to it, so how many lone pairs do we have to put around it? Well, we've got to put 6 electrons or 3 lone pairs around it. Okay, and we're going to do the same here. Now let's just draw out, well, let's actually just count up a number of electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And because of that, each of these 2 oxygens having 1 bond too few, we give this a negative charge, and this is because of something called formal charge. We'll talk about that a little bit later on. So you'll see that a heteroatom, nitrogen, oxygen, fluorine, chlorine, bromine, that sort of thing, when that has 1 bond too few, it gets a negative charge. When it has 1 bond too many, it gets a positive charge. Now let's go down to NH4 plus here. This is just protonated ammonia. Nitrogen, of course, has to be the central atom, and there really isn't any other way for my hydrogens to be arranged other than right around it. And so this is the Lewis structure for ammonia, for ammonium, this NH4 plus, except we've got to figure out exactly where the plus charge is. How many bonds did we say nitrogen likes to make? Well, that is 4. That's 3, and it's making 1 bond extra here. It's got that 1 load of an extra bond, so it bears the plus charge to tell you it's a little bit unhappy. Just as these oxygens are a little bit unhappy too, because they're bearing 1 bond too few. Let's talk just a tiny little minute about formal charge. The ideal situation is where your formal charge, which is really just a representation of the stability of your atom, you want a formal charge of 0. So there's a formula for this. Formal charge is simply the number of valence electrons, not the number of valence electrons, hang on. The number of valence electrons minus the total of the number of bonds to that atom plus the number of, the number of bonds to that atom plus the number of lone pair electrons on that atom. Don't mean lone pairs, I mean lone pair electrons. So carbon, for example, valence electrons is 4. Number of bonds to that carbon is 4. Can you guys see how many lone pair electrons are on that carbon? Well, that's 0. So the formal charge of that carbon is 0, meaning it's happy. Look at this oxygen here. Valence electrons in oxygen is 6, minus how many bonds to that oxygen? Well, it's 2. It's 1 double bond. And how many lone pair electrons there? Not lone pairs, but lone pair electrons. That's 4, giving you a formal charge of 0. That oxygen is also happy. But when we go to this one, and then these two are actually the same, we have 6 minus the number of bonds to that oxygen is 1, plus the number of lone pair electrons attached to the oxygen, which is 6, giving us a formal charge of -1. And 2 formal charges of -1 add up to a formal charge total of -2. So that is a little bit about drawing Lewis structures for neutral molecules and ions, and a little bit about formal charge too. Okay, thank you.